Math 265A, Cuesta College. I'm Joe Vasta. And in this lecture we're going to cover part 2 of section 3.11. So we're doing some related rates, and we're looking at this problem here, which is number 12 in the book, shrinking square. The sides of a square decrease in length at a rate of 1 meter per second. So the first thing that I want to draw is a square. So I've got the square. I also want to note the word decrease, which I would have figured out if I was looking at this shrinking square. And it says the sides of a square decrease in length at a rate of 1 meter per second. So I have to call the sides something. I'll just call them x. And they're all the same. So x, x. I can put an x there and an x there. So that's my first thing that I'm going to put down here. dx dt, that's the change, the rate of change for the sides, happens to be 1. Except it's decreasing, so we're going to say -1 meters per second. Okay, so meters x second time. Okay, there's two problems in one here. The first part says, at what rate is the area of the square changing when the sides are 5 meters long? So this is part A. And they're asking, at what rate is the area of the square changing? Okay. 5 meters long, that's what the sides are. So this is x equals 5 meters. We're going to color code this. So that will make it orange. We'll make it blue. And so we need a formula that has the area of the square. So can we come up with a formula for the area of the square? And it is area equals side times side, or side squared. And the sides are x, so x squared. Okay, so now what I want to do is I want to take the derivative of both sides with respect to t, with respect to time, and that's what I'm going to do. So apply d dt to both sides. Okay, what is my goal here? It says, at what rate is the area of the square changing? So we want to know, before we continue, I'll put the goal up. We want to know what dA dt is. So that's the goal. I'll circle it. And let's go ahead and zap both sides with the derivative gum with respect to t. So the derivative of a is 1. But then we have to put a dA dt because we're taking the derivative with respect to t. So this is dA dt equals. Now on the right hand side, we are taking the derivative of x squared with respect to t. So the derivative of x squared is 2x. And then we have to put the dx dt. Now in the implicit differentiation, we would take the derivative with respect to x on both sides, and we wouldn't have to put that because it's just a dx over dx, but this time we put that. So I have this equation here that has rate of changes in it, and I know two of these variables. See, there's one variable, dA dt, two variables, the second variable is x, and the third variable is dx dt. So I know dx dt I also know what x is. So dA dt equals 2 times 5 times dx dt. Dx dt is -1. So this is going to give me -10. It's the area that's changing, and area is measured in, we have meters, so area is measured in meters squared, and this is per second. So if the sides are decreasing in length at a rate of 1 meter per second, then the area is decreasing at -10 when the sides happen to be 5. Now when the sides are different, like if the sides had been 3, the answer would have been differently. So the answer would have been different. So the area, the change in the area is actually changing over time. And so we have that right there. Now had we put the units in here, we said 5 meters, and then this is -1 meter per second, we would have seen that would have been meters squared, and on the bottom would have been seconds. Let's go ahead and do part B. And maybe you want to do part B on your own by pausing the video. So we'll put part B right here. At what rate are the lengths of the diagonals of the square changing? The length of the diagonal. So let's draw one of the diagonals. There are actually 2 diagonals of this square. The other one goes the other way. And I'm going to label that just some letter. I'll label it D for diagonal. At what rate are the length, or let's just say at what rate is the length of the diagonal of the square changing? So the other time it was the area that was changing. Now it's the diagonal that we're looking at. We're going to look at dd dt. Some of you are thinking you should not have called it D, because now this is very confusing, but there's the letter, there's the diagonal, that second D. So you could call it something else. You can call it Z or Y if you like, and it would be like dz dt or dy dt. So that's what I'm looking for. Okay. So we have a diagonal, and we have an x and an x. Is there a formula that we can come up with that has an x and a d in it? So we're looking at this picture here, and maybe this will help you. That happens to be a right triangle. So we'll use the Pythagorean Theorem, which says x squared plus x squared equals hypotenuse squared. So this is d squared. So what I have is 2x squared equals d squared, and I'll switch it around here. D squared equals 2x squared. I'm going to go ahead and take the square root on both sides. This is going to give me d equals plus or minus the square root of 2x squared. Well, the diagonal happens to be a positive measurement, so we're just going to go with the plus. And since x is positive, the square root of x squared is just going to be x. So my formula says the diagonal equals the square root of 2 times x. Okay, so that formula was a little bit tougher to get to than the area. Okay, that we just kind of wrote it down. We were ready to zap both sides with the derivative gun. Now I'm ready to zap both sides with the derivative gun. The derivative with respect to t. Okay, so the derivative of d is 1, and then we have to write dd dt. And the derivative of constant times x is just the constant. And then we have to write dx dt. Okay, so this is my goal right here, d dt. There it is right there. And I know what dx dt is. That was given. I'll circle that in blue. So it looks like dd dt equals root 2 times negative 1. So what does this give me? This gives me negative root 2. Now the diameter is measured in meters, so we're going to say negative root 2 meters per second. And that is how we do these problems here. I'll box the answer. And notice, like when the sides of the square are decreasing, so will the area, and so will the diagonal. And all those are negatives, which means decreasing. So that takes care of problem number 12 from the book, shrinking square. Let me see if I can find the other. Here's the piece of paper. The next one we're going to do is problem number 14, which is shrinking isosceles triangle. So let's take a look at that. Some of you may want to pause the video and see if you can do 14 on your own, but if not, it's no big deal. Let's go ahead and take a look at what we have here. We have a shrinking isosceles triangle. The hypotenuse of an isosceles right triangle. So it's isosceles right. And then it says it decreases. So you got to remember to put a negative. In length at a rate of 4 meters per second. So let's draw the picture here. I'll draw the picture right here. It's a right triangle. So it looks like this. It's isosceles, which means the legs are equal in length. And we could just label those legs some letter, like maybe X. It says the hypotenuse. So we have many choices in terms of letters that we can use. I'll just use an H, though I can see you using like a Z or something else. And it says the hypotenuse decreases in length at a rate of 4 meters per second. So this is a rate of change. This is saying dH dt. And we have to be careful because it says decreases, so I'm going to write minus 4 meters. That's what the hypotenuse is measured in, per second. So why don't we go ahead and give this a color. I'll circle it in purple. And that's going to be used to solve A, B, and C. So A, B, and C, they're all their own problems here. So let's go ahead and do part A. Part A says, at what rate is the area of the triangle changing when the legs are 5 meters long? So they want to know the rate, at what rate the area is changing. So the area we'll call A. What they're trying to figure out is dA dt. So there's my goal right there. And this has area in it, and we should also mention that the legs measure in part A 5 meters. So it's kind of like the last problem. I do have an x equals 5 meters for the last problem. You would think they would switch some numbers around when they're writing the book problems, but oh well. So let's come up with a formula that has the area and the x. Do we know a formula for the area of a right triangle? Well, the area of a triangle is 1/2 base times height. So the area of this triangle is 1/2 base, which is that guy, x, times height, which is x. So the area equals 1/2 x squared. So why don't we go ahead and zap both sides with the derivative gun with respect to t and see what that gets us. So this is d dt and on here, I'll just move it the work over here. So the derivative of a is 1, but now we're doing with respect to t, so this is going to be 1 times dA dt. This equals the derivative of 1/2 x squared. The 2 comes down, and so when you're done with that, this is going to be x dx dt. Okay, so we have that right there. We have x. This is the guy I'm trying to solve for, dA dt. But look what I have here. I have dx dt, and I don't know what that is. I never figured that out, so it's going to need a different color. I'm going to circle that in green. Okay, so is there a formula that I can come up with that has x's in it and maybe something else, or maybe x's and h's? And the answer is yes, it's the Pythagorean theorem. So over on this side of the line, here, I'll take it over here. I'm going to use the Pythagorean theorem on this triangle, and I'm going to say x squared plus x squared equals h squared. So it's kind of like before, where we did it with, we had the same thing. It said x squared plus x squared equals d squared in the last problem, and we ended up, I'm not going to show you the work again because we had already done it. This is going to give me h equals the square root of 2 times x. So now I'm going to hit this equation with the derivative gun. D dt. The derivative of h is 1, and then you have to go dh dt. dh dt. This equals the derivative of root 2x is root 2. And then we should put a dx dt. And let's see, so we're kind of doing this off to the side because we had another unknown that we didn't think we were going to get, but now we have it here. So look what I have. I have a dh dt, which was given in the problem. Look at this. This is given in the problem. I also have the dx dt, which I don't know, which I need it for that spot right there. So let's go ahead and put the -4 from here in there. So we have -4 equals root 2 dx dt. So I'm solving for dx dt, so I'm going to just say dx dt equals. Now what do I have to do? I'm going to divide by root 2. So this is going to be -4 over root 2. Now, this can be simplified. I don't know where I'm going to simplify it, because I'm running out of space here. I'll just do it right here. I can simplify this by rationalizing the denominator. See, if this was like a 7 on top, negative 7 on the top, I probably wouldn't do this, but because it's a 4, watch what happens. I'm going to rationalize the denominator by multiplying top and bottom by root 2. So what does this give me on the top? Negative 4 root 2 all over root 2 times root 2 is 2. Then of course those guys cancel, and I end up getting dx dt equals, let's see, that's going to be negative 2 root 2. So that looks a lot more simplified than negative 4 over root 2. So I have negative 2 root 2. And that's what we have, dx dt is that. And you know, if you wanted to put units on that, that would be x is measured in meters, and then time is seconds. So I'm going to go ahead and circle that whole thing in green. Now I know what that is right there, and I know what the orange is. So do you see how I do the extra work over here to get another variable, which was the dx dt, and I did that. So let's go ahead and continue this. This is dA dt. Now I'm back to this other problem. This equals 5 times negative 2 root 2. We could put the units in there, and maybe some of you will, because they will help you with the units on this, but we can see its area, which is probably going to be meters squared, over time, which is seconds. So we can just put that in at the end. And in fact, look at this, dA dt is negative 10 root 2, and we'll put the meters squared per second. So there's the answer. So that was a little bit tougher than problem 12, and that answers part A. Part A is right there. At what rate is the area of the triangle changing when the legs are 5 meters long? And so that's what it's changing at. Now we don't want to put this in our calculator in round unless they ask us to round. Okay? So when they don't ask you to round, usually at this stage, at this math, the math level you're working at, you want to put the exact answer. Part B says, at what rate are the lengths of the legs of the triangle changing? The lengths of the legs, well, that would be dx dt. That's what they're looking for. But look around here. Do we have a dx dt? And the answer is, yeah, here's your dx dt right here. So this right here is the answer to part B. We have it right there. So it already has a green circle around it, but we'll box it anyway. So there's the answer to part B. Part C says, at what rate is the area of the triangle changing? So I thought we probably already found that, but look, when the area is 4 meters squared. Okay. We've run out of room here, so I'm going to get another piece of paper. And what are they asking for on part C? They're asking for dA dt. Okay. But not when x is 5. So let's go ahead and put part C. They're asking for dA dt. That's the goal. And that is when the area is 4 meters squared. So area is 4 square meters, or meters squared, you can say. And so we need another color for that one. So I think I will choose blue. Okay, so once again, we're going to do this whole thing with the area equals 1/2 x squared. So I'm going to rewrite it here. So the area equals 1/2 x squared. I hit both sides with the derivative gun. And you know what? This is exactly what I did right here. Okay, so I can actually just look at my answer here. I have dA dt equals x. I'm looking at this right here. dx dt. Okay. Now I know what the x dt is because we computed it right there. Now you might think, well, we know what x is. Isn't x 5? Well, that x was 5 was only for part A. For part C, the x is going to be a different value because the area is 4 meters squared. So x couldn't be 5 and the area be 4 meters squared. So this x, and maybe it's the way they wrote this problem, how they had to go A, B, and C. Maybe it would have been better if they had just included more problems and just changed things around. Because I know a lot of people are like, let's just put that 5 right there and it's going to be nice and simple. But no, they told us something different. They gave us this area equals 4. So I'm going to circle x not in orange because that's not what the x value is going to be. I need a new color. We'll use red. So we know dx dt is -2 root 2. So this one right here is -2 root 2. Well, what is x? Well, we don't know yet. And what we're looking for is dA dt. So just like part A, when we got here, we got stuck. And we had to figure out what the green thing was. Now we're stuck here, we know what the green thing is, and we have to figure out what the red thing is. Now in order to do this, let's take a look at this area equation. We have the area equals 1/2 x squared. That's this equation right here. Well, they told us the area. They told us the area is 4. That right there can get replaced with a 4. So can we find out what x is in this equation? Yeah, we can. I'm going to multiply both sides by 2. And I'm going to use the square root property. I'm not going to put plus or minus because x is a positive measurement. This is root 8, which can be simplified to 2 root 2. So that is what x is, 2 root 2, and it's meters. And we're going to plug that back right here. So this is 2 root 2. So we just have to go ahead and multiply 2 root 2 times -2 root 2. This is going to give me 2 times -2 is -4, and then root 2 times root 2 is 2. So it looks like my final answer is going to be -8, and I have to get the units correct. This is going to be meters squared per second. And that completes part C. This one's probably one of our tougher problems here because, it was, the x changed. But that's how you do problems like this. And notice all of our rate of changes that they ask us for. dA dt is negative. The x dt is negative. dA dt here is negative. They're negative because the triangle is shrinking. And so that is what we have. So let me see if I can find the next problem. The funny part about it is the next problem is not going to be as difficult as this problem. Here it is. In fact, problem number 14 might be the most difficult problem in part 2 of this lecture. So here is problem number 16. Expanding cube. So the cube is growing, and this is good. All of our rate of changes are probably going to be positive. The edges of a cube increase. So things are growing. That's going to be positive at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So, I mean, you can draw the cube on this. Of course, with the way I drew it, for some of you it may be popping in and out, you know, because this has got, it's an optical illusion thing. But the cube, you know, here's x, and here's x. There's no part A, B, and C, thankfully. You might try to do this problem on your own. It is going to be simpler than problem 14. Okay, our goal. How fast is the volume changing? So our goal is dV dt. Okay, let's go put our givens. It says the edge of a cube increase at a rate of 2 centimeters per second. So the edges are x, so x is increasing at that rate. dx dt equals a positive 2 centimeters per second. Out of tradition, we've been circling some of these givens in different colors because it helps us. How fast is the volume changing when the length of each edge, that would just be x, is 50 centimeters. So we'll go ahead and use green for that. So do we know a formula that has v's and x's in it? Volumes and the side of the cube? Yeah, we do. Hopefully you know that the volume of a cube is length times width times height, or just x times x times x, x cubed. Zap both sides with the derivative gun. D dt. The derivative of v with respect to t is 1, and then we have dv dt. This equals the derivative of x cubed is 3x squared. This is with respect to t, so we're going to say dx dt. Let's get our colors going again. The dx dt, we know what it is. The x, well, we have an x squared here, but we know what that's going to be. And we're looking for dv dt, that's our goal. So dv dt equals 3, x is 50, so we have 50 squared, and dx dt is 2. And so when you crank this out, maybe you put it in your calculator, maybe you do this by hand, you end up getting 15,000. And we have to put our units, so volume is measured in centimeters cubed per time per second. Once again, if you had kept your units here, you would have had centimeters squared there because you have the squared, and then you would have had centimeters per second, and you would have got the same thing. So there's the answer. Now these problems seem kind of dumb. You know, you have an expanding cube. The next problem we're going to have is the shrinking cube. And they really seem dumb, but once we get to part 3, you're going to see the application. I mean, that's when you start seeing airplanes landing and people flying kites and important things that you would see in the real world. But we need to take baby steps before we hit those problems, and those problems will be done in part 3. So here's another problem that seems pretty worthless, kind of, but it helps us so we can do those other problems later. Shrinking cube. The volume of a cube decreases. Okay, so there's going to be some negatives here. At a rate of 0.5 feet cubed per minute. Okay, so those are our units. The volume decreases. So let's just write this one up here. This is dV dt decreases, so this is negative 0.5. So you can write that as 0.5. I'm going to write it as 1/2. 1/2 feet cubed per minute. Now we could draw another cube if you'd like. We don't have to do that. Okay, so there we have the cube. And this is new information here. So why don't we go ahead and circle it. And hopefully we'll use that. What is the rate of change of the side length when the side lengths are 12? So what is our goal? Our goal in this is the rate of change of the side length, which is dx dt. Okay, so that's what we're looking for. And it says when the side lengths are 12, the side lengths are x, and they equal 12 feet. So we'll go ahead and circle that in a different color. And the formula that has volume, because we have volume here, and that has x is the same one we used last time, which is v equals x cubed. I'm going to zap both sides with the derivative gun, d dt. We're going to go through this one a little faster because we did exactly the same work on problem 16. dv dt equals 3x squared dx dt. So let's see what we have here. dv dt, we know what that is. I'll circle that in brown. That's negative 1/2. And we know what x is, so we'll know how to do x squared. And there it is, dx dt. We don't need to cough up another equation. We can finish this problem. So I have negative 1/2 equals 3 times x squared dx dt. Negative 1/2 equals 12 squared is 144. 144 times 3, I believe, is 432 dx dt. I'm going to divide both sides by 432. And so when I do that, I'm going to have to multiply that by 2, and it's still going to be negative. So my final answer here, dx dt, that's the one I'm looking for, is negative 1 over 864. And we have to put the units. This is x, which is measured in feet, per the time is minutes in this one. So we don't want to put seconds, we're going to put minutes. There's the answer for problem number 18. So that's how you do these problems. One more problem for part 2, and that's going to be problem number 20, which is called expanding rectangle. So you have a rectangle that's growing. A rectangle initially has dimensions 2 centimeters by 4 centimeters. So that's weird that they would be telling us that. Let's just draw that. 2 centimeters by 4 centimeters. All sides begin increasing in length. Okay, that's pretty weird. At a rate of 1 centimeter per second. So what's going to happen after a few seconds? It's going to look like this. And these are going to be variables, so we might as well call this top one length and this shorter one width. Okay, all sides begin increasing in length at a rate of 1 centimeter per second. So the width is increasing at 1, and so is the length. So we better just put all these guys up. So dl dt is 1 centimeter per second. dw dt is also 1 centimeter per second. We better color code those. So this guy right here is blue. That guy right there we'll make red. And we have to continue to read the problem here. At what rate is the area of the rectangle increasing after 20 seconds? So they want to know the rate of the area. Okay, so they want to know this. This is our goal. dA dt. And they also tell us that we're at 20 seconds. So t is 20 seconds. So we'll circle that. Let's go ahead and kind of cough up an equation that has W, L, and A in it. Well, wouldn't that just be area of a rectangle? So we'll do that right here. Area of a rectangle equals length times width. We're going to hit both sides with the derivative gun with respect to t. The derivative of A is 1. And this is with respect to t, so we're going to go dA dt. Over here I have to do the product rule. The derivative of the first, dl dt, times the second, which is just w, plus the first, which is L, times the derivative of the second, which is dw dt. Now notice what we have here. We have this is the blue one right here, which is cool. We know what that is. Here's the red one right here. But we don't know what the width is and what the length is. So we have to figure that out. 20 seconds. So let's think about this. Let's go ahead and work on the length and the width. So we need more values here. Well, the length is 4. And if this rectangle is increasing of all the dimensions by 1 centimeter per second, 20 seconds have gone by, then this is not going to be 4 anymore, but it's going to be 24. And same with the width. If the width is 2 centimeters and the width has a rate of 1 centimeter per second, then after 20 seconds we're going to not be at 2, but we're going to be at 22 centimeters. So let's take out some more colors. So that's 24, that's the length, which will go right there. And 22 is the width, which will go right there. So now we can find dA dt, which was the goal. dA dt is 1, that's the blue part, times the green part, W is 22, plus L is 24, and 1. So this just gives me 22 plus 24, which gives me 46. This is area over time, so this is going to be centimeters squared or squared centimeters, because that's what we have. Centimeters is what we're using. Over time is seconds. So that's how you do problem number 20. This completes part 2 of section 3.11. Do your homework. Have a good day. I'll see you in the next video.